Hi, my name is Holman, and I'm a first-year physics PhD student here at Columbia. I'm here to report on a new project in Sebastian Will's research group, aptly named Tweezer. Our group is working to realize a programmable atomic tweezer array, which has many applications in quantum computation, quantum simulation, and quantum optics. In particular, this poster focuses on the quantum computing capabilities of our platform. First, I think it is important to clarify what quantum computing is, and how our platform fits into the current landscape. Quantum computing has great potential to solve problems deemed classically intractable, but is still in its infancy as an applied technology. Currently, superconducting solid-state devices dominate the landscape, primarily from existing classical infrastructure, think silicon, but other platforms, including trapped ions, quantum dots, and more recently, neutral atoms. For our platform, we trap neutral strontium atoms with high-powered lasers and arrange them into arbitrary arrays. Neutral atoms have lots of advantages over other hardware platforms, including but not limited to all qubits being identical, the qubits are long-lived, and we have the capability of generating arrays with hundreds of qubits. The types of problems quantum computers can solve are of incredible import for many diverse fields. One use case is solving the NP-hard problem of determining the maximum independent set, or MIS, for a given graph. An independent set is a set of vertices that have no two adjacent, while an MIS is simply the maximum number of vertices for a given graph. This computational problem has a significant number of applications, primarily related to resource allocation. One pertinent example is setting up accessible vaccine distribution centers to cover the largest population possible. As you can imagine, trapping individual atoms is not the easiest of tasks. It requires an incredibly high vacuum to not just isolate, but also hold atoms for a long time. We first heat up the atoms to free them from a solid source and capture them using optical methods involving magneto-optical traps. This initial trapping creates a reservoir from which we can populate our eventual target array. Unfortunately, due to physical properties of the traps, we only have a 50% chance of trapping an individual atom, which leads to rearrangement protocols that are necessary to generate a clean array. Finally, we can operate and read out the results. Returning to solving the MIS problem, I'll discuss two unique algorithms. First, the quantum adiabatic algorithm slowly evolves the system for it to end up in the lowest possible energy state. The classical cost function can be seen to map well to the physical properties of the system, such that two atoms do not want to be both excited and neighbors. In particular, we use a unit disk representation to map an arbitrary graph to a geometrical one in free space. Second, the quantum approximate optimization algorithm uses a hybrid classical and quantum approach. To prepare the quantum state, we use multiple parameters, such as laser intensity, detuning, and phase, all varied over some time period. By varying these and observing the final independent set size, we can use classical optimization algorithms to find the maximum independent set. This algorithm works particularly well for large arrays that might take too long for QAA to reach the ground state. Finally, I'd like to thank my research group for all the amazing work they have done this past year, even in spite of the pandemic. I'm excited to contribute to the quantum technology landscape, and then happy to have the opportunity to share our progress. Thank you for listening, and please feel free to reach out to me to follow up or to answer any questions you may have. Thank you.